talk about motion in fields. So first we'll start out just with a magnetic field. We'll have a particle moving along inside of a magnetic field. So let's say we have a positive charge, and the positive charge is moving towards the top of the page. Let's also say we have a magnetic field pointing into the page. Okay, so velocity towards the top, field into the page. The direction of the force then, by the right-hand rule, would be towards the left of the page. Okay, not so bad. So let's think about what happens to this little charged particle, this positive charge. After a little while, well, its velocity would have had it going towards the top of the page, but now there's a force that pushes it to the left. So it's going to be deflected. Its velocity is going to change. It's going to be a little to the left. But let's think about the force on it now, at this new point. Now it has a velocity a little bit to the left. The magnetic field is still into the page, so the force is no longer going to be to the left. It's going to be a little down from that. So that's going to deflect the velocity a little bit more. And let's continue that pattern. So one more point, to another point, to another point, and if we keep going, what we'll see is that each little deflection causes, in the end, circular motion. And if you look at each point, the direction of the force is toward the center of that circular path. Well, if we have a force acting towards the center of a circular path, we have a name for that. That is a centripetal force. In this case, where we have a positive charge traveling through a magnetic field, the magnetic force on that charge is a centripetal force, and the object moves in a circle. Now, that might seem like, what does it matter? That's actually very important for a lot of different applications. This is how particle accelerators get charges to move in circles. This is one reason why solar flares move in arcs. Another thing to notice is that at every location, the force is perpendicular to the displacement of the particle. Okay, well, what does that mean? Well, this is going to seem like a non sequitur, but let's think about work. Work is equal to F times the displacement times the sine of theta. Now, let's think way back to what that theta means. That theta right there in that equation is the angle between the force and the displacement. Now, I just said, in this example, the angle between the force and the displacement at every location is 90 degrees. Okay, well, what's the sine of 90 degrees? 0. So, at every location, the work being done by the magnetic force is 0. The magnetic force does no work on the charged particle moving in a magnetic field. Magnetic forces do no work. That's the ultimate point. Magnetic forces do no work. Also, in every location, the particle has a centripetal acceleration. It experiences a centripetal force. It has a centripetal acceleration, but it always moves at a constant speed throughout this case. As long as the magnetic field is constant, the speed is constant. So, 3 big points. If you have a charged particle moving through a magnetic field, the charged particle will experience circular motion. The magnetic force does no work because the force and the displacement are perpendicular at every location on the circle. And the particle moves at a constant speed throughout its path. Okay, something else we can do. We can figure out the radius of this path. So let's try that. So we've got this situation where it's moving in a circular path. I've said that the magnetic force is pointed towards the center at every location. We've shown that. If it's pointed towards the center, like I've said before, it's a centripetal force. Well, let's see. If the magnetic force is the centripetal force, that means that the magnetic force, FB, is equal to the centripetal force, FC. They're the same thing. They have to be equal. So, FB, the magnetic force, well, we know that that's equal to QVB sine theta. We also know that the centripetal force, we have an equation for the centripetal force. The centripetal force is always equal to mv squared over r. So now I've got an equation. QV b sine theta equals mv squared over r. Let's see. Let's clean this up a little bit. What shows up on both sides? V. Cancel out a v. All right. Theta, in this case, is always equal to 90 degrees. The angle between the velocity and the magnetic field is always 90 degrees. So sine of 90, that's 1. So we get QB equals mv over r. Well, let's solve for the radius, r. That is equal to mv over qb. So there we go. The radius of the path is equal to mv, the mass of the charged particle times the velocity of the charged particle, divided by qb. Q being the charge on the particle, and b the magnetic field strength. Think about one more thing. Let's think about what would happen if you had a charged particle that was moving at a constant speed. Well, that's the case we've already looked at. Just moves in a circle. Now, what would happen if you had a particle that, for some reason, was increasing its speed? Well, what would happen? Well, let's look at our radius equation. R is equal to mv over qb. So I'm increasing the speed. The only thing I'm changing in this equation is v. And if we increase the speed, if we increase v, what happens to r? It gets larger. We increase v, we increase r. So, if you increase the velocity, increase the speed, the radius will get bigger. It will move in a circle of larger and larger radius. In other words, it will spiral outward. Now, in the other case, if there's decreasing speed, well, that means v is getting smaller and smaller and smaller. If v is getting smaller, r is getting smaller. The radius of the path is getting smaller and smaller and smaller, and it spirals inward until, if v gets to be 0, the radius is 0. And it just stops and sits there. Okay, let's take a moment to review electric fields now, because we're going to start adding electric fields into the mix. Electric fields. Electric fields are caused by electric charges. They move away from, the electric field moves away from positive charges and moves toward negative charges. If you put a charge into an electric field, it will feel a force. And the magnitude of the force is given by this equation. F is equal to Q times E. Now, if we put a positive charge in an electric field, a positive charge will feel a force in the direction of the in the direction of the electric field. A negative charge will feel a force in a direction opposite the electric field. And we can see that from our equation. If Fe is equal to Q times E, the direction on both sides of this equation has to be the same. So let's say the electric field was to the left. So E is to the left. If Q is a positive charge, then F also has to be to the left. If E is to the left and we have a negative charge, then Fe has to be in the opposite direction of the electric field. It has to be to the right. Okay. A positive charge will feel a force in the direction of the electric field. A negative charge will feel a force in a direction opposite the electric field. So let's look at an example where we have two charged plates, positive charge, negative charge plate, and outside of that we have a region of magnetic field. Also, the negative plate has a little hole in it because we're going to plop a little positive charge right next to the positive plate, and that positive charge is going to feel a force away from the positive plate, and it's going to accelerate towards that negative plate. We're going to aim it right so it goes through the hole in the negative plate. And then it's going to enter the region of magnetic field. So, inside of these charged plates, there is an electric field, and that electric field causes a force on the positive charge, and that positive charge accelerates towards the negative plate, and it moves in a straight line because it's feeling a force directly towards the negative plate. Now, once it enters the magnetic field, it won't feel an electric force anymore. It will feel a magnetic force. Well, what's going to be the direction of the magnetic force on a positive charge moving through this magnetic field? Well, you use your right-hand rule. And if you use your right-hand rule, you'll see that it will be deflected like this. Okay. Now let's put some numbers in there. Let's say that there is a potential difference, a delta V, of 50 kilovolts between the two plates. And let's say that there's a magnetic field strength of 0.350 Tesla in this magnetic field out here. And let's say that this little charge is a positive charge. In fact, let's say it's a proton. And I want to know two things. I want to know the speed of the proton once it enters the magnetic field. So right as it goes through that hole in the negative plate. Well, there's a couple ways we can do that. We could use energy conservation. We could also go to our IB equations. And IB is nice and gives you an equation to solve this. They give you 1/2 mv squared is equal to q times v. Or q times delta v in this case. We know delta v. We know Q of a proton. Q of a proton is 1.60 times 10 to the negative 19 coulombs. We know the mass of a proton. It's always 1.67 times 10 to the negative 27 kilograms. And then, therefore, we can solve for V. And if you solve for V, you get 3.1 times 10 to the 6 meters per second. That's how fast the proton is moving when it leaves and goes through that hole in the negative plate. Now let's find the radius of the path once it's in the magnetic field. Well, we have an equation for the radius of the path. Let's go through that again. We equated the magnetic field and the centripetal force, because in this case, the magnetic force is the centripetal force. So we get QVB sine theta equals mv squared over r. And we got v's on both sides, so we cancel those out. Also, theta in this case is 90 degrees. If you have a charged particle moving through a magnetic field, the angle between the velocity and the field in this case is 90 degrees. So we get QB equals mv over r. If we solve for r, we get QB over mv. Oh, excuse me. We get mv over QB. And if we solve for the radius of the path, we get 10.8 meters. So that was a case where we had one region of electric field, one region of magnetic field, and they acted on the particle at two different times. First electric, then magnetic. Let's consider a case where they both act on the particle at the same time. And this is a case called the velocity selector. It's very popular with IB. So a velocity selector, in a velocity selector, you have an electric field and a magnetic field that are set up in the same region, and they are perpendicular to each other. So you have one whole region where you have an electric field in one direction and a magnetic field perpendicular to that. So I'll draw a picture of that. And we're going to send a charged particle. Let's make it positive. We're going to send that charged particle with a velocity through this region, through this velocity selector. So it has a velocity v to the right. Let's think about the forces on this particle. Well, there's an electric force because there's an electric field and a charge. The charge will feel an electric force, in this case towards the bottom of the page, because the electric field is towards the bottom of the page and it's a positive charge. It will also feel a magnetic force, because there's a moving charged particle in a magnetic field, so there will be a force on that charge. And that will be towards the top of the page. Okay. So this charged particle feels an electric force towards the bottom of the page and a magnetic force towards the top of the page. Well, if those two forces are equal in magnitude, the net force on that positive charge is 0. If we have the same amount of force towards the top of the page as towards the bottom of the page, those two forces cancel out, and the net force on that positive charge is 0. So let's say we have that case. Let's say we have the case where the magnetic force and the electric force are balanced. Let's see if we can come up with an equation for what that would look like. So if we have that the magnetic force is equal in magnitude to the electric force, that means that QVB sine theta is equal to Q times E. Well, let's see, how can we clean that up a little bit? Well, there's Q's on both sides. Let's cancel the Q's. So we get VB sine theta is equal to E. Let's also make another assumption. Let's assume that the velocity and the magnetic field are perpendicular to each other. If that's the case, theta equals 90 degrees, and the sine of theta is 1. So we're left with VB is equal to E. If we solve for V, V is equal to E over B. Okay, what this means is if the two forces, the magnetic force and the electric force, are balanced, this must be the velocity of that particle. Let's go back to our equation of QVB sine theta equals QE. Let's think about this. Let's say our particle is going really, really, really fast through there. What would that change about this? Which side of the equation would it change? It would change the left side. We'd have a greater magnetic force. If the particle moves faster, V is larger, the magnetic force is greater. If the magnetic force is greater, then the forces aren't in balance. The particle, in this case, the case that we've been looking at, the particle is going to drift upwards towards the top of the page. So it won't travel in a straight line. It'll drift upwards because there's a greater magnetic force. If the velocity is very small, that means the magnetic force is very small. If the magnetic force is very small, that means that this positive charge would drift towards the bottom of the page. Only when the velocity is equal to E over B are the two forces in balance. And only when the two forces are in balance does this charged particle move in a straight line through the velocity selector. That's why it's called a velocity selector. That's what it does, is it picks out only the charged particles that would move in a straight line. All the charged particles that are moving too fast, they'll drift in one direction. All the charged particles that are moving too slow, they'll move in the opposite direction. Only the ones that are moving at the exact right velocity will move in a straight line. So a velocity selector allows you to select particles that are moving at a very specific velocity. Okay. Now let's put it all together into a mass spectrometer. Mass spectrometers are very important instruments in the world of science. Not just physics. Chemists love them. They're used in biology as well. They're used all over the scientific world. A mass spectrometer is what you have. Well, at its basis, it's a velocity selector, and then the particles move through the velocity selector, and after that they pass into a region of constant magnetic field. So what that means is you're shooting particles through the velocity selector. Velocity selector does its job. Only particles with a very specific velocity can pass through, and once they reach the constant magnetic field, they'll be deflected. They'll start to move in a circular path. And the way it's set up is that they'll go in a semicircle, and they will hit a wall. And there are sensors along that wall that detect where those particles impact. And then, based on the radius of the path, you can determine the mass of the particles. Because these particles going along, they move in semicircles. So you can figure out the radius. You know R. Well, we can go back to our good old equation. R is equal to mv over qb. Well, if we know R, and if we know the velocity, because they went through that velocity selector, so they must have v equal to e over b. If we know the velocity, and if we know the charge on them, and if we know the strength of the magnetic field, we can calculate the mass. And that's very important, because it's difficult to measure the mass of very small objects. It's hard to take a tiny little cesium atom and put it on a scale and measure the mass of it. So instead, when they're measuring the masses of molecules or something very small, they'll use a mass spectrometer.